Okay, I will start now. So this is the last lecture. Today I wanted to talk about non-singular curves or non-singular points on curves. Point is that if you have a non-singular point on a curve, the local ring has a special structure. It is called, it is called a discrete valuation ring, which means that in some ways it works like you are used in complex analysis for holomorphic functions. Every rational function or every regular function at this point has a certain order of 0 or order of pole, and you can work with that. So the valuation, the valuation of the named discrete valuation ring corresponds to the order of pole or 0 of the function, and that can be then used to do many things. The whole last chapter of my lecture notes is about what one could do with that if one had time, but I will not cover it. So by definition, a curve is a variety of dimension 1. So now let a non-singular point. Then we will show that the local ring at P is a discrete valuation ring. First, obviously, I will also have to tell you what that means. So we have take some preparations in algebra. First, we need the Nakayamas Lemma, which is one of the most standard lemmas in commutative algebra. So let that for a ring M an A module, and so if I in A is an ideal, we already had this in some form, we denote IM to be the submodule of M, which is just a set of all Bm with B and I and M. And this is an A module. And take instead of make a submodule by multiplying with an ideal. So now we have Nakayamas Lemma. So it usually comes in two parts. First, I state the second part as Nakayamas Lemma, and the second part, the first part is Nakayamas Lemma, and the second part as some corollary. But sometimes you also have both together as the statement. So this is one of the more important statements about local rings. So let A be a local ring. M. So maybe as a local ring, it has a maximal ideal. So with maximal ideal small m, and let M be a finitely generated A module. Okay, we need it to be finitely generated. So now we have this change condition. If M is equal to the submodule M, so small m times M, then M is equal to 0. So that means, so if the module does not become smaller by taking elements in the maximal ideal instead of general elements in the ring, then it had to be 0 to begin. Okay? So, and one needs all assumptions. If, for instance, the module is not finitely generated, the statement is false. And you certainly need it's a local ring. So, proof. So, by contrast, we assume that M is finitely generated, but it is not 0. So assume M is different from 0, and we also assume it's finitely generated. And we take a minimal set of generators. Let I1 until AR be a minimal set of generators, as a module, obviously. So it's finitely generated, so it's generated by finitely many elements. And I choose one set of generators with the smallest possible number of elements. So now, so of M as a module, obviously. So then, so we know that, for instance, the last one, the last generator, UR. So I mean, the trick will be, I will find, under this assumption, I will find a set of generators which is one smaller, and then it's a contradiction. So in fact, I will eliminate the last one. So as UR is an element in M, which is the same as M times M, I can write UR is equal to the sum I equals 1 to R, Mi times Ui, where Mi are elements in the maximal ideal M. Okay, and now I can bring this one term here to the other side. So we get 1 minus MR times UR is equal to sum I equals 1 R minus 1 Mi UI. But now I claim that 1 minus MR is a unit. Namely, if not, then I can write 1, which is equal to 1 minus MR plus MR. So this lies in the maximal ideal, and this lies in the maximal ideal. So this would lie in the maximal ideal, and that's certainly nonsense. And so this 1 minus MR is a unit. And so we can multiply its inverse, so it follows that UR is equal to sum I equals 1 to R minus 1 Mi times 1 minus MR to the minus 1 times UI. And so you can see that UR is in the span of the UI until R minus 1. Thus, already. 1 until R minus 1 generate. So it's a very simple indirect proof, but it's a very useful lemma. Now, as I said, it has a second part, which I call corollary, which is a statement which is maybe more commonly called Nakayamas Lemma, a criterion for a set of elements in a module M to be a set of generators. So again, let A be a local ring, maximal ideal M, and M, and you write A to be the quotient A mod M. So let large M be a finitely generated A module. So assume, so let assume we are given some elements F1 to Fr in the module M, such that their classes in M mod M times M, so such that their classes F1 to Fr M times MM generate M mod MM as K vector space. So note that M mod MM is a natural way a K vector space. Any element in A will, if you multiply by an element in A, if this element lies in M, it will act by multiplying by 0. So what really acts on M mod M is K. So so M mod MM is an A module, but A acts via its quotient K. Because the action of M is by multiplying by 0. So if they generate as a K vector space, then they generate. Then F1 to Fr generate M as A module. Okay, so one has this criterion for elements in a module to generate it by just looking at the quotient by the maximal ideal. And that turns out to be useful in many contexts. So, okay, and now we want to prove that by reducing it to the previous version of, so we prove. So we put N to be the submodule generated by F1 to Fr in M. Submodule. The aim obviously is to prove that this is equal to M. And we consider the A module, the quotient M mod N. We want to show that M is equal to N, so we want to show that this module is 0. So we note that if we take n mod mm, by definition, n mod mm is the vector space generated by the classes f1 to fr, and this is the same as m mod mm. So this is equal to m mod mm by our assumptions. So thus, if we kind of add this back, take n plus mm, this is the same as m plus mm. So therefore, what happens if we multiply by m? Take m times, we want to show obviously that if I take m times m mod n, this is equal to m mod n. So what is it? So this is m times, if I want, m plus n modulo n. No, because this is just m. What? Now it should be trivial. So I say, now, because this is just by definition, no? This is m times, so if so this is precisely what it gives by definition. This is m, if you want, this is m times m modulo n, but I have to make sure that n is contained in it. So the way this works is that this gives me m times m plus n. So you take m times m, and you add to it n, so that n is a submodule, and you divide by it. This is how one does this quotient. But we know that m times m modulo n is just m. And so we are in the situation of Nakayamas lemma. We have assumed that m is finitely generated, so Nakayamas lemma applies, so by Nakayamas lemma. We have that m mod n is equal to 0. That means m is equal to n. Okay. So this is this statement. So now I want to come to the statement with this discrete valuation ring. First, I have to explain to you what a discrete valuation ring is. So definition. So let A be a local ring which is also an integral domain. So without zero divisors. So A is called the discrete valuation ring if it has two properties. So, and I will obviously not always want to write this, so in future this is always dVr. If first the maximal ideal in A is a principal ideal. Maximal ideal M is a principal ideal, so that means M is equal to T for some T in N, some element T in M, and such an element will be called a uniformizing parameter. And the second statement is that every element in the ring can be written as a power of T. If T is a uniformizing parameter, any element of A can be written as a power of T times a unit. Parameter. Every A in A can be written as A equal to U times T to the N for U in a unit and N a non-negative integer. So, I mean, uniformizing parameters are not unique. You can easily see that if you multiply uniformizing parameter by unit, it's again a uniformizing parameter. But this is the description. Okay. So, from the definition as an exercise, you can, for instance, easily show that if A is a DVR, and T a uniformizing parameter, then say, and N is some positive integer, so then the ideal generated by T to the N is equal to M to the N for all N. But also, now we want to show the statement I was making at the beginning, that the local ring of a non-singular point of a curve is always a discrete valuation ring. Now, as I want to use Nakayamas Lemma, I will have to show that certain ideals are finitely generated. So therefore, I want to see that the local ring is Noetherian, and this is actually a very simple exercise which you can try to do. So let X be a variety and P a point in X. Then local ring of X at P is Noetherian. So the idea is just that first you can obviously assume that X is affine because P has a neighborhood which is affine. And then you know that to be Noetherian means you have a ascending chain of closed, a descending chain of closed subrights, which corresponds to a descending chain of ideals. So first you get that this affine variety is Noetherian by having the fact that finally kx1 to xn is Noetherian. And then you can somehow see that if you have an ideal in A of x, then you can look at the ideal generated by this in the local ring. And if you have a descending chain of ideals, so somehow you can go back and forth between these ideals. So the ideal here in AX and the ideal in the local ring, and they correspond. You only have less ideals here than you have there. And so if every chain of ideals is terminates here, it will also terminate here. Anyway, it's an easy exercise, but by what I say, it's even. So, and now we just use this. So let P be a non-singular point on a curve C, then this local ring is a discrete valuation. Okay, so let's try to prove it. So we have to obviously use it's a curve, and we use our and it's a non-singular point. So let MP in the local ring be the maximal ideal. So we know that P is non-singular. So C has dimension 1, so the tangent space also has to have dimension 1. So we know MP modulo MP squared, and the dual vector space of that has dimension 1. So thus, the dual vector space to MP mod MP squared, which is also a K vector space. So if the dual vector space has dimension 1, then also MP mod MP squared has dimension 1. Is a one-dimensional K vector space. So let's take any generator of that, or rather let T be an element of M such that the class of T generates MP mod MP squared a vector space. Then we want to claim that T will be a uniformizing parameter. Okay. In fact, that is clear. So, because we can just directly apply Nakayamas Lemma. So, by Nakayamas Lemma, so rather this second part, this what I call corollary, we get that MP. So, as an ideal is just a submodule of being an ideal in OCP is the same as being a submodule of OCP. So thus we get an MP is just generated by T, because the statement is that T generates, so the class of T in MP mod MP generates that. Nakayamas lemma says that then the T itself generates MP as, say, if you want, as OCP module, which is the same as an ideal. So, and this just means that it is a, so thus, according to our definition, T is a uniformizing parameter. So this was the first requirement. Now we have to show the second statement, namely that every element can be written as a unit times the power of T. And this is not completely automatic, because you could think that you kind of could need arbitrary, higher and higher powers. And it never ends. But let's see. So now we want to see that what I just tried to hint doesn't happen. Now we want to see that if I put M, the following module, or ideal, is intersection of all n bigger than 0 of the mth power of n. So, if we should be able to write everything as a power of t times a unit, then this must be empty. I mean, must consist of 0. No? So, because an element which lies in this infinite intersection would not be, you would not be able to write it as a times a finite power of t. And so we want to show, so we define this, and we want to show that this is equal to 0. And for this, again, we apply Nakayamas lemma. Now the first statement. So M is an ideal in OCP, which is Noetherian. Now we need this Noetherianity assumption. We also needed it before. Anyway, it's Noetherian. So thus M is finitely generated. So just by definition, we have, if we take M times M, this is equal to M. Because here, if you multiply this by M, you get the intersection over all n bigger than 0, M to the n plus 1, but that's the same thing. So thus, by Nakayamas lemma, so thus, we must have every element A in the local ring must lie in, say, the maximal ideal m to the power n without the maximal ideal of the power n plus 1, sum n. No? There's no element which lies in the intersection of all of them, so then each element must lie in one and not the next. So, but according to what we said, but I had as this exercise, as m to the n is equal to the ideal t to the n, it follows that this A must be of the form t to the, u times t to the n with u an element in OCP which does not lie in M, because otherwise we would be in M plus 1. So with u in OCP without M. And we know that all the elements in a local ring which are not so anyway, it has changed, but M was always MP. So I write it just to. So U lies in the local ring, but not in the maximal ideal. But in a local ring, all the elements which do not lie in the maximal ideal are units. And so this proves the statement. Now, I told the name of such a ring is a discrete valuation ring, and this is because, not very surprisingly, it has a discrete valuation. And so I have to explain to you what that is. It's not a big mystery. If you can write any element as A in the ring as u times t to the n, and this number n is the valuation of the element. And so, but at least it would be good, it's also good to keep in mind what the interpretation is. So we have a valuation on this local ring which associates to every P. What one could call the order of vanishing. Of F at P. So like in complex analysis, if you have a holomorphic function and you have a point, then it can have a certain order of vanishing there. So which is some integer, and so you can do the same here. And as in the case of holomorphic functions, you can also here deal with rational functions, and then you can also have an order of pole. And so that that we will see later, that this valuation can be extended to the whole field of rational functions on the surface. So let me first, however, give the definition. So let again P be a non-singular point on a curve C. So we define valuation nu p from, we look at anyway, most likely I mean, obviously, if you look at the statement here, it cannot be quite correct because it doesn't apply to the element 0. So we want to, like this. Every element A without 0 can be written like this, because obviously 0 we can't write as a unit times t to the n. So we, therefore, our valuation goes from OCP to the non-negative integers, and it sends valuation of a function f will be the number n, where whenever f is equal to u times t to the n for u a unit and f a uniformizing parameter. I mean, it's straightforward to see that, so recall that being a unit just means that u of p is non-zero. And now, check this is well defined. As I said, there are many uniformizing parameters, but it's easy to see that two uniformizing parameters just differ by multiplying by unit, and so there's no problem. Okay. So, and this map nu p is what one calls a valuation. So this is actually a certain standard concept which rule in also in algebraic geometry, but so some and in number theory, or if you when you construct things like the p-adic numbers. So it satisfies the following properties. So nu p satisfies properties. First, if I take a product, it's additive. Then this non-Archimedean property, if I take the sum of two elements, the valuation of that is at least the minimum of the valuations of the two of them. So it's bigger equal to the minimum of nu p of f and nu p of g. And it is equal to this minimum if these two valuations are different. Equality of f not equal but different from nu p of g. And the third property, nu p f is equal to 0 if and only if f is a unit. So the last statement is obvious, no, because the way we defined it. Then one is also basically obvious. No, we can write, so let f equal to a times t to the n, g equal to b times t to the m, where these uniformizing parameter a and b are units. Then first, obviously f times g is equal to a times b times t to the n plus m. AB is a unit, so this directly says this number 1. And second one is also, so one of these two valuations must be smaller or equal to the other, so we assume the first one is smaller. So smaller or equal, so we assume that n is smaller or equal to m. Then we can write f plus g. What is it? This is a times t to the n plus b times t to the m. So I can write this like this. So maybe, so it's even. So maybe write it like a times this times 1 plus b divided by a, or b times a to the minus 1 times t to the a minus m times t to the n. No? This is, it's just a times t to the n plus b times t to the m. I write it like this. But now I can see that if m is bigger than n, then this expression is a unit. By the same argument we had before, if it was not a unit, as we are in a local ring, it would be in the maximal ideal. But if we subtract from it b divided by a t to the m minus n, which certainly lies in the maximal ideal, I get 1, and I would get 1 lies in the maximal ideal. So it's the same argument, so therefore this is a unit. And so this shows it. Now, as I said, so one of the points of this discrete valuation which is useful for us is that we can extend it to the field of rational functions on C. So we get somehow doubt that I have enough material for 1.5 hours, but you maybe will not be too unhappy. So, so we can extend this new P to rational functions on C. So how we do this? So we know that Kc is equal to the fraction field of the want, well, now I write AC, but I mean, so, okay, so, so obviously, so if, say, C0 in C is an open affine subset, non-zero, non-empty open affine subsets, then Kc is equal to Kc0. No? That we know. And so in Kc0 is just K, so of, it's just, we take the regular functions on a C0 or the coordinate ring, and we take its quotient field. And now, obviously, I can assume that P is contained in this. So then we have that the local ring of C at P, obviously, by our definition, is a subring of the field of rational functions, but it also contains AC by definition. And so you can see now, if you take the fraction field of this will be, if you take fractions of fractions, they are still fractions. So this will be a subring of this, which contains this whole thing. So it follows, if I take also equal to the fraction field of the local ring. No, I just write a fraction as a fraction of fractions. And as all the elements of which I originally took the fractions are already contained here, I don't get anything bigger. So what did I want? Yeah. And now we extend the valuation from OCP get bigger, so without 0. Get bigger equal to 0. So from KC, again without 0, to whole integers by just saying that nu p, define nu p of a fraction f divided by g of elements in the local ring as nu p of f minus nu p of g. As I said, this is supposed to be the order of the function. If it's negative, it's supposed to be the order of pole. So obviously, the order is the order of the numerator minus the order of the denominator. So now, obviously, you have to see it's well defined. Maybe I can check it because something I have to check. This is well defined. Here. So if f divided by g is equal to f prime divided by g prime, by definition, this is equivalent to the statement that f g prime is equal to f prime g in OCP. And so, thus, of f g prime is nu p of f plus nu p of g prime is equal to nu p of f prime plus nu p of g. And so if you bring this to the other side, you see that you get the same. Okay, and now maybe, as I already said it, I can write it. So let point. So if f if nu p of f is bigger than 0, we say f has a 0 of order f. If smaller than 0, we say f has a pole minus up of f. As one would have for meromorphic functions in the complex plane. And all this has kind of the obvious properties. So let me just state it. So first, we can, instead of saying it like this with the quotient, we can also directly again apply it, say that f can be written as a unit times t to the n, where n is this order, but now the n can be positive or negative. So let p a non-singular point on the curve C. First, let f be an element in the function field, which is not 0. So we say that then nu p of f is equal to the number of n, integer n, if and only if there exists a unit u in the local ring such that f is equal to u times t to the n. Just as simple as that. And another simple statement is the elements which lie in the local ring. So the elements in Kc which lie in the local ring are precisely those for which the valuation is non-negative. So nu p. So the local ring Cp is equal to the set of all f. So maybe without 0. Is equal to the set of all f in Kc without 0, such that nu p of f is bigger or equal to 0. So in terms of evaluation, we can precisely say which functions are regular, which also is already reflected in how we call things. So this is, these are actually rather obvious definitions. So by our definition, up of f is equal to n, if and only if we can write f equal to say u1 times t to the l divided by u2 times t to the m for some units, u1, u2 units in OCP. And now the L minus M should be N. But obviously nobody can hinder us to divide these two units through each other to get a unit and then multiply the powers out. So this means f is equal to u1 times u2 to the minus 1, which is a unit, times t again. And you can obviously go backwards. Okay, so that's not very, and the second statement is a even simpler. Nu p of f is bigger or equal to 0. if and only if we can write f is equal to u times t to the n, where n is bigger or equal to 0 and u in OCP unit. So that means u is a unit, t is an element in OCP, so this is a product of elements in OCP. There's nothing there. Okay, and so these are both in the local ring, so that's here. Again, you can go backwards. Okay, now there's, so the theory of curves is a bit based on this, but now I have only time for one application, also because then the more complicated ones require much more preparation, which is that if we have a morphism from a curve minus so assume you have a non-singular curve, you take away one point and you have a morphism from this curve minus this point to a projective variety, then it extends to the whole of the curve. And this is another, I will say it again, but anyway, this is another way of somehow maybe seeing that projective varieties are complete in the sense that there are no points missing. So if you have this map from this curve to this thing, there's this one point in the curve that you don't map. Now, but all the same, so you have a hole in the curve, but this hole will still go somewhere in the projective variety, and that point is not missing there. You can put it back. So I will explain it again in a moment. But so they have the following theorem. Curve non-singular point. So let without this point y the morphism to a projective variety. Then extends morphism. Phi from C to Y. Okay. So let me first prove it and then maybe say a few more words. And it's really something about curves that we need all the assumptions. So let's see how we use them. So first, I have assumed that y is projective. So we have y subset n is a closed subvariety. Okay. So if we extend phi to a morphism phi from C to Pn. So if a priori we don't know that the last point, that this point actually goes to y, but it might in theory go to somewhere else in Pn, then I claim we can deduce it goes to C, and we get a morphism to C. Then, if I take the inverse image under this new phi of y, so y is closed, This is a closed subset of C, and it contains C without 0. Without P. So thus, I mean, it must be, so this is an open-dense subset, so thus it follows that phi to the minus 1 of y is equal to the whole of C, and so phi from C to y is a morphism. So thus, we can assume that our target is Pn. Okay. Now, we know how morphisms to Pn are defined. They are defined by equivalence classes of tuples of rational functions, if you remember. So then we can write our original phi can be written as, say, f1, f0, say, to fn, where the fi are elements in Kc. And now, what we have to show is that this phi is defined at P. Okay, so a priori, we have just this, and now we want to show that phi is defined at P. The condition for this was that there is a representative, so this is equivalence classes, so up to multiplying by a rational function, by a non-zero rational function, so that there is a representative, so that not all of them vanish at P, and all of them are defined at P. Okay? And so we have to see that. And somehow, what we can do is by multiplying these things by suitable powers of a uniformizing parameter, by a suitable power of the uniformizing parameter, so the right power, we can achieve that. So let T be a uniformizing parameter at P. So we write Ni for the order or the valuation of Fi at P for I equal 0 to n. So we choose an I0 for which we get the smallest possible number. So we choose I0 n such that Ni0 is equal to the minimum of the Ni for I from 0 to n. And I claim that if we multiply with t to the minus Ni0, we get precisely the right power, so that the map will be both defined and so that all the functions will be defined and not all of them 0. So we put I equal to t minus Ni0 times Fi. Then The first thing is the valuation of I is equal to Ni minus Ni0, which is bigger or equal to 0. And this means that Gi lies in the local ring, so that the function is defined. Defined at P. And so all Gi are defined at P, so this is for all I. On the other hand, if I look at the special one, Gi0, of Gi0 is obviously equal to Ni0 minus I0 is equal to 0. So that means Gi0 is a unit in the local ring. So but what are the units in the local ring? These are precisely the functions which do not vanish at P. So we have precisely the assumptions that we need for this to be defined. So, so these are all defined at P, and at least one of them does not vanish. So this is fine. So thus, thus if we take our map phi, which was f0 to fn, is also equal to G0 to Gn, because we have all multiplied all of them by the same rational function, is defined at P. Found that our function can be extended in this way. Okay. So, as I said, I can maybe try to draw a picture or something. I mean, it's not so clear, but it's really somewhat this is actually, I mean, this statement here. So I had defined completeness for you, and I'd proven that projective varieties are complete. And this statement that you can extend a morphism from a curve minus a non-singular curve minus a point to the curve to a projective target is equivalent to the statement that this y is complete. It's a different formulation of it, which is useful for many purposes. Anyway, just to make the picture, so we have here our curve C. We take away this one point P, and we have here our target Y, and it will somehow map into it. Somehow the curve goes into it. We don't know what it does. And this point P is somehow missing, so I have here a missing point. But the point is that in Y, this point actually exists, so we can put it back. Now, if for instance we take if we take Y and if we would have something like it could be that for instance Y is this thing, and we have taken away so some curve like this, then this point would be missing, and we can't put it back. Or if we have a fine, if you have a fine space, maybe this curve, this point somehow goes to infinity, and then we also can't put it back. So that's really, and so this we can say in these examples. So we need all the assumptions. So statement is not true if either Y is not projective, or C is not a curve, but of higher dimension, or if P in C is a singular point. So all these statements we need, so we can give some examples. For instance, just a simple thing, if we take phi from, say, A1 without the origin to, well, I could say A2, but I could also have made it A1. I just sent a point A to, say, 1 over A comma 0 or something like that. Then this is a morphism, but it obviously cannot be extended to A1. So we see that we somehow need the projectivity, because somehow this point wants to go to infinity, and that point is missing at infinity. We can also, even in the projective case, we can yeah, okay. Now, I didn't write this very well, but okay. So we take phi from then we take our Caspar cubic, z of y squared minus x to the 3, to say 1. So origin 1 or A1, but I mean, like this, it only goes to A1 anyway. So I mean, just to A1 in P1. I mean, so I claim this can also not be extended. So here I just sent an element, A, B. I sent to, so B is the y coordinate. I sent to B divided by A in A1, and then if I want to go to projective space, I take the usual embedding via U0 into P1. And this is a morphism, but we know it cannot be extended to, I mean, this morphism cannot be extended to this point. Because otherwise it would be an isomorphism. I mean, anyway, so this cannot be extended. Whole zero set. It is by itself. You could, as a, that you have the inverse map, just the projection, and so if you could extend it, it would be isomorphic, but this one is singular and this one is not singular. And anyway, we also have seen that this is just a rational map given by a rational function, which is not regular at the origin. Okay, maybe that's enough. Then an easy corollary, which is basically just a reformulation, is that if C is a non-singular curve, and P from C to Y a rational map, and Y is projective, then phi is a morphism. And this is clear. Phi is defined on an open dense subset of C, but as C has dimension 1, the closed subsets are finite. So phi is defined on C minus some finite set of points. So, and then just we use the previous result. So inductively extend phi from without, say, for some n, Pn until Pr to C without Pn plus 1 until Pr. So that's just by using the previous theorem. We can always extend, we had seen, if it's defined on a curve without one point, then it's defined also in that point. So we take as our curve here the original curve minus whatever n minus r points, and then we extend it to one of these points, and we keep on going until it's defined everywhere. Okay, and so as a corollary, if two smooth projective curves are birational, then they are isomorphic. So that's basically, so we have, if we have a rational map from one curve to the other, then as the target is projective, it will extend as a morphism from one to the other. The inverse, as it's birational, the inverse map is also a rational map, but it's also a morphism. So in fact, they are isomorphic. No, we just need that both are projective and both smooth. And obviously, this is only true. Okay, I think. Is there anything more? And this is something only about curves. In higher dimension, this is certainly false. I mean, it's so this is not true in higher dimension. We have, for instance, seen that P2 is not isomorphic. P1 times P1. But they are birational. I mean, if one knows a little bit more, one can show in general, in arbitrary dimension, if two varieties are birational to each other, then they are two open subsets, one in one and one in the other, which are isomorphic. And let me maybe be slightly more careful. If I have a rational map from one variety, from a smooth variety to another smooth variety, then the locus where it is not defined has codimension 2, so has dimension 2 less than the dimension. So, so that one can prove in general, and then this statement becomes a special case. But a priori, we have. Okay, maybe that's for the moment as much as I wanted to say. Finally, I did more or less use my time. So, are there questions? I think I will make one more set of exercises so that you can also practice with tangent space and that stuff, and then I mean, I maybe, so I think we already, we should maybe still discuss when the final exam, when you want the final exam. I mean, what you propose. I mean, it's, I'm rather flexible, but on the other hand, you might want it not too soon, but also not wait forever, so that you have no chance to forget everything. So maybe you can think about it and say something, but otherwise, I don't know, do it in 2-3 weeks or something. Okay, I can try that. Mm-hmm. Yeah, yeah, it is. I mean, that is. I mean, that we already know. This follows from the if you remember, we had as a consequence of the fact that the diagonal is closed, we had this statement that if we have two morphisms from one variety to another, which agree on a dense open subset, then they're equal. And so the extension is always, if such an extension exists, it's always unique. This follows from the separatedness, so which is that the diagonal is closed. But that also exists is a consequence of the completeness, or in this case, projectiveness. Okay. So thank you then, and now I can indeed wish you a good weekend. There's no surprise that you say,